Okay, so let's start. So that's what we did last time. We talked about Perceptron. Hopefully everyone understands that. I want to run through some of the key things that we said before we continue. So we talked about this online mistake-driven algorithm, very simple algorithm. The way I present it here is one of the two alternatives that we had, where I'm showing that we update both W and theta. And then we talked about the theorem, the mistake bound. The important thing about this is you want to know that there is a mistake bound. You want to know what it depends on. It makes sense, I hope. And you want to understand that we really didn't make any assumption beyond linear separability. We didn't go through these details. What we did is we said, even though the original theorem was only for linear separable cases, in fact, it's robust. And so there are two things that are important here. One is that it's robust to noise. Even if the data isn't completely linearly separable, it's going to work. You'll see this in your problem set that I'm going to discuss a little bit later. And the other thing to remember is how we quantified it. That's important. So think about here, make sure you understand how we quantify the lack of separability, right? So this function, max between 0 and gamma minus y dot product, is important, and you'll see it in a few slides again. It's an important function, so we want to make sure that we understand it. If y, the label, times the dot product is greater than gamma, it means that the data is outside this strip of width 2 gamma in this case. If it's inside it, or actually moving to the other side, then this guy is going to be positive, and therefore the slack is going to be positive, which means there is some penalty that you want to incur. And as a function of that, we said we can actually quantify how bad or how worse it's going to be when Perceptron encounters data that is noisy or non-linearly separable. Okay, so from that we moved to talking about some practical issues. I mentioned a couple. The key is regularization. We're going to talk about it a little bit later today. Really the idea that in addition to just minimizing the standard thing that we're talking about, number of mistakes or other loss functions, we also want to maintain simplicity, and this is what regularization is doing. So one key ways to do regularization in the case of online algorithms like Perceptron is what is called average perceptron. And we ended up with discussing some intuition for what makes a classifier good. And hopefully you got convinced that if you have a linear classifier, or any classifier for that matter, that runs over a long stretch of examples and makes no mistakes, it's pretty good. If it makes mistakes after 3 examples, not as good. Again, the assumptions that we are making here is that every data point that you see is sampled uniformly, independently of other data point you samples from the same distribution. So it doesn't matter that I already spent half an hour learning. Still, where I am, I want to be able to have a hypothesis that is robust to a long stretch. And that's the intuition that leads to this algorithm. I fixed the typo that was here last time. Basically, I'm not going to reread this algorithm because you saw it and you'll see it again in the homework. The basic idea is that you run the Perceptron. You can run any other online algorithm instead of the Perceptron. You have your weight vector. You run it until you make a mistake. If you haven't made a mistake, you just keep the same hypothesis. Once you made a mistake, you record how many examples this hypothesis survived, because it's some measure to the quality of this hypothesis, and you put it aside, you update it, and you start running with the new hypothesis. Once you made a mistake, you record how many examples this one survived. You put it aside, you update it, and you keep on running with the next one, and so on. At the end, what you'll get is you'll get a bunch of linear functions, linear vectors, the hypothesis, each one with a count of how many examples it survived. Again, a measure of how good it is, or an estimate of how good it is. And the way you're going to make your decision is this way. So you're going to average them with the CI. In the problem set, you're going to implement this. You're not going to implement it exactly this way. I'm going to leave this for you to think about. This way, you may have to carry with you way too many vectors, VIs in this case. And you don't want to do it for two reasons. One, memory-wise, you cannot do it if the dimensionality is large. Two, every time you want to make a decision on example X here, it means that you have to first evaluate it on all K that you kept on the side. It's going to cost you time. So you will, as we suggest in the homework, you'll implement it slightly differently in a more clever way, and you'll only have two weight vectors to keep. Questions? Okay. So and I think you'll see that this is actually a good algorithm. We'll see what happens. Okay, so a few other things that you can do. One of them is what is called Perceptrons Margin. The idea is that we care about not just learning a linear separator, a hyperplane that sits between the purple points and the red points. We would like to prefer to place there a thick separator. One way to do it is to force in the update to do it. So I'm going to promote, I'm not sure if I used this term before, promote and demote. So in Perceptron, I'm either adding the example X to the current weight vector, I'm going to call this promotion, or I'm subtracting the weight vector, the example X from the weight vector, I'm going to call this demotion. So rather than promoting and demoting relative to theta or relative to 0, I'm going to invent one other parameter. I'm going to call it gamma again, and I'm going to promote only if the dot product minus theta is actually less than gamma, and demote if the dot product minus theta is greater than gamma. So I'm going to be a little bit more strict. And in this way, I'm going to force something like this. Again, this algorithm works very well, better than the standard Perceptron. There is a little bit of caveat here, which you may not understand at this point. We're going to discuss it a little bit later next week when we talk about SVM, that in principle, this gamma, the contribution of this gamma could disappear. It's what is called the functional margin. Once W becomes a larger vector, because you add stuff to it all the time, the relative importance of this gamma might disappear. In practice, though, it works quite well. We did not ask you to implement this version in the homework just because there's enough to do anyhow. You can feel free to do it if you want to play with things. Here is another extension that you may care about. So let's assume you run your Perceptron. you made a mistake on this example X. What do? You update. It so happens that this example X comes back again. What will happen now? Yeah, you have to check. You're going to predict on it. What do you think is going to happen? You don't know. Someone knows?
Wouldn't depend on like what you see after you classified X. If you're
Let's say you didn't see anything. It was 2 consecutive X's.
then you should not make a mistake if you updated the vector.
Would it depend on the learning rate?
So it's not known, basically. It's not guaranteed that you will not make a mistake on it, even though you corrected, because you may not, maybe you haven't corrected enough. And maybe this is disappointing to you. I just saw this and I corrected and I'm still making a mistake. What's happening here? So you could change the learning rate so that this doesn't happen. So this is called, has some name, aggressive perceptron, where essentially you're changing your learning rate in such a way that actually you will not make the mistake on this example immediately if it comes again. I mean, later in the future, I don't know what happens because maybe you spoil the W again, but at least immediately you're guaranteed that you'll make it. You can also think about it as if when you saw X, you introduced X to yourself multiple times. As long as you made mistakes, you updated until you stopped making mistakes on X, and then everything is fine. So this changing the learning R, and you can do the algebra yourself if you want to make sure, is a way to basically do this if you care about this. Okay, so there's a lot of other extension. I'm going to put here a shameful plug to a software package that my group has developed over the years. It's a very good package for linear classifiers, has all the bells and whistles, has several classifiers, Perceptron, Winnow, Naive Bayes, a few others, Grad. And this is something that you can play with if you're interested in these kind of classifiers. Okay. So let's move back and step first one step back to something that we've already seen. Stochastic gradient descent algorithms. So in fact, in the introductory class, we introduced a very simple learning principle. I have some loss function. I want to minimize it. And I'm going to do it with stochastic gradient descent. Specifically, this is what we said. We have a set of examples. Over there, I'm denoting it Z, which are the pairs X, Y. Sample from some distribution over X cross Y. I'm trying to learn a linear function parameterized by the weight vector W. What do I want to do? I want to minimize my risk function. And my risk function is this J here, which is the expectation over Z, or X cross Y, of my loss function Q. Of course, we cannot do this because we don't know this probability distribution. So we estimate it by taking M examples and averaging our loss. That's what we do. In stochastic gradient descent, we approximate yet another way by not really computing this and the gradient relative to this, but rather doing it incrementally, one example or a small group of examples at a time. And what we get is the following update rule. We've seen that. The weight vector at time t plus 1 is going to be the weight vector, the previous weight vector at time t, minus some learning rate and the gradient of this loss function. I'm going to lose the loss function and just call it G, gradient in time t. So this is a very general framework, and from that point, the difference between algorithms really amounts to choosing the loss function Q. So, okay, this is just notation. So, so this is the same thing again. I'm just spelling out z here as x comma y at the top, so you will remember what I'm talking about. Q is our loss function. Remember, it depends on x, y, and w, the current w. On the other hand, we have a learning rate, and this is the gradient. Okay? So now, as we said, there are many loss functions that we can think about. We talked about LMS, least mean square, which is y minus the dot product all square. And we differentiated it and developed this update rule here. This is, by the way, an algorithm from, I think, 40s that is called Widrow-Adeline, again, introduced in the context of neuroscience. Notice the difference between what this does and, say, what Perceptron does. Right? So even though we're making predictions, binary prediction, right? So the way you predict is you take the dot product and you take the sign of it. Right? If it's positive, you say yes. If it's negative, you say no. Nevertheless, in the loss, you just take the dot product. So it's y minus the dot product. You don't do the sign when you compute the loss. Okay? Here's another loss function, a common loss function. It's called hinge loss. And this loss function should be familiar to you because we just repeated the introduction of it a few minutes ago. So here we look at the max between 0 and 1 minus y dot product. And we talked about this as a way to measure how far the point x is from the thick margin. Notice one difference that I put here is, from what I introduced before, what's the difference between this function? Let's see if you remember visually, yeah? Instead of gamma, I put here 1. If you think a little bit about it, and we're going to see this multiple times again, it doesn't matter. It basically amounts to scaling everything. It doesn't matter whether I call it gamma or I divide everything by gamma and call it 1. Everything is going to be okay. So how does this look? So this is a picture that we've seen. It's a graph of loss functions. The x-axis is the dot product, wx, and the blue line, hopefully you see blue line here, that the arrow points to, is this function. So once it's greater than 1, this function is 0. And below 1, it grows linearly. So now, if you think about it, this actually leads, if you take this loss function and use the stochastic, the gradient descent rule, it leads to perceptron. You differentiate it. Now, there is a little bit of a problem here. You could complain and say, I don't know what to do in this point, right? The gradient will cause problems, so we call something like this subgradient, and it doesn't matter, really, this point. You know that in this area, you're going to get 0, and you know that in this area, 0 means no updates, translated to a mistake-driven algorithm. No mistakes, no updates. And in this area, it's going to grow linearly with x, which is what I have here. So if the dot product times y is greater than 1, again, dot product, if it's positive and y is positive, this product is going to be positive. Moreover, I want it to be greater than 1. If the dot product is negative and y is negative, this also is going to be positive. Nevertheless, I want it to be greater than 1, so I'm a little bit more strict. So if everything is fine, and maybe a little bit more than fine, greater than 1, not only greater than 0, no mistake by a margin, then no update. Otherwise, updates, and you update relative to the gradient, which is a linear function of x. More specifically, this is the gradient. It's negative value yx. Okay, so if y is positive, you subtract x. If y is negative, you add x. That's it. So that's perceptron. Okay, and so far we talked about, I gave you 2 examples. We'll see a few other examples. In fact, you've seen another example already in the previous problem set. In all cases, we kept the learning rate R fixed. So RT was equal to R. What I want to introduce now is an algorithm that changes the learning rate. Changing it in a way that is interesting, basically taking into account some historical information. This algorithm is called ADAGRAD for adaptive gradient. And basically the intuition is that if you have features that happens a lot and change all the time, so the gradient is always active, you want to pay less attention to them. If you have features that are infrequent, you want to listen to them when they change. That's kind of the intuition. So I want to learn slowly from frequent features, but pay more attention to rarely changed features that are informative. So how do we do it? What we're going to do is we're going to define a per feature learning rate. And it's going to work this way. So notice the indices here, right? So I'm adding more indices. This G is a vector. The W is a vector. T represents the time. Where are we in the iterations? And J represents the feature of this vector. So I have G, Tj, and W, Tj. So what do? I'm defining a per feature learning rate this way. So R, again, T, comma J, is going to be my fixed R, think about it as 1, divided by this capital G function. This capital G function is the sum of all squares of the gradient over time. So I'm running from the first iteration up to the current iteration, the tth iteration. Okay? So that gives me this update rule, right? So it's W at t plus 1 at coordinate j is the tth at coordinate j minus the new gradient times this learning rate. So what does that mean? The easiest way to think about it, okay, so first of all, this algorithm is good. It's going to update weight faster than the standard perceptron with and started than the LMS. The important thing to think about, or the easiest way to understand what's happening is to actually think about it in the case of perceptron with Boolean features. So let's assume our features x is only 0 and 1. So let's sit on one feature that was always 0. So far, it was always 0. If it's 0 now too, in the tth example, nothing happens. What you will get here is basically all the g's. Remember that the gradient in perceptron is basically yx. So if x is 0, the gradient is 0. So it's going to be sum of zeros here. So what I'm going to get here is 0 over 0. Nothing happens. Let's assume that this is now the first time that something happened. X is 1, xj is 1 now. So I get 1 here, and the sum is also 1. Next time this happens, when I get 1, this is going to be larger now. And therefore, the effective change is going to be smaller. Okay? So as long as nothing happens, I don't touch it. once static start to happen, I'm updating, and then with time I'm going to update at a slower rate. Yeah.
We made the assumption that noise is bad. So when we have noise, will this algorithm be very susceptible to noise?
Okay, so that requires a proof that it adapts to some level of noise. You will see in the homework that it does. So of course, if there's a lot of noise, everything is going to suffer here. With reasonable amount of noise, actually, it's going to be robust. So this is something that is typically very difficult to prove how well algorithms like this, or in general, learning algorithms tolerate noise. But there are some works that show that it does. Yeah, yeah.
So the frequency of the word that was used over there, I guess it only refers to Boolean features, because if the features were not Boolean, say if it could be 100, I mean, that would affect the big G more than like the features that are.
So it's true that different scales of the features will affect you in principle, you would think. But this will adapt to it, right? Because it's for every feature, it's doing it separately. So the same is going to work for real valued features. It's just easier to understand what's happening in Boolean features. And in fact, many cases, so by the way, so this is a good algorithm. This is a relatively new innovation, I think 5-6 years. This is the most commonly used version of gradient descent that is used today also in neural networks, with a slight variation that is called Adam, but it's really Adagrad. And it's the only version that I know of that actually has some theoretical support. So people can prove for this version that actually it's doing well. And you will see in your problem set that it does. Okay, a couple other things that we are adding. So we talked about loss functions. Really, so currently we have loss functions, and we differentiate the loss functions to get update rules. Really what happens in practice is that we don't just take the loss function as is, differentiate and get the update rule. We add another component to the loss function. So this is our loss, the Q here. In addition, we add this R component and some weight here to decide whether we want to pay a lot of attention to this guy or not so much attention to this guy. And this is called regularization. The idea is that it will force the learn function to be simple. And I put simple in quote because what does simple mean? So at this point, I'm going to show what we do. And next week, we'll start understanding why this makes sense. So what do we do? What are these R's that we're adding? So I'm giving you 3 loss functions. LMS, we've seen this before. Inge loss, we just saw it. And logistic, which is this loss function. I also showed the graph of it earlier. It's the red one here. And then we can add these regularization components. It turns out that whenever you add regularization components, these algorithms have names. In some of them, they are old names. So if you take LMS and add as R of W, right? So R, the regularization, depends on the weight vector that you have. If you add sum of squares, square root, so I denote it here as L2. I hope you've seen these notations. If you haven't, I'm going to define, I'm going to see it again later today, and I'm going to give a definition. This is L2 square, which means the sum of square of the coordinates of W. This turns out to be an old algorithm called ridge regression. If, on the other hand, instead of L2, you add L1, which is just the sum of absolute values of the coordinates, you get an algorithm that is called lasso. In the case of hinge loss, which we just saw, typically people would add, again, L2 square. This is an algorithm that is called support vector machine. You probably heard about it. You will see it again, and you'll see it also in the homework. In the case of logistic regression loss, which is this loss, E1 plus E to the y dot product, negative value of y dot product. When you add L2, it's something that is called logistic regression. Now, I want to emphasize that these algorithms, in most cases, were invented independently of this perspective. Most important example in this slide is support vector machine that was invented in the 80s, completely differently. People did not think about it as a as a stochastic gradient descent algorithm. In fact, the implementation was very different. Only, say, in the last 10 years or so, people realized that it's exactly the same as doing this. And today, most of the modern implementation are doing that. Yes?
Yeah. I had a question that when I compare the hinge loss equation with the LMS, why does the hinge loss have the extra y multiplying? Like, because if the weight transpose times x is like a prediction of y, why are we multiplying the rate of y times the prediction of y?
Let's see, what does it do here that we multiply it? What does y times the dot product give me?
The dot product gives us a single number.
Right. And it could be either negative or positive. If it's a negative example, y is negative, negative 1. If you did not make a mistake, the dot product is also negative, so this product is positive. If it's a positive example, y is plus 1, and if you did not make a mistake, w dot product x is also positive, so this product is positive. So this product is positive if and only if you did not make a mistake. So okay? You see that? It's positive if and only if you did not make a mistake. Otherwise, it's negative. And so this is a compact way of writing the behavior that you want. Compact in the sense that you write the case of positive example together with the case of negative examples. So take this as homework. Write this down for yourself for the case of negative example, for the case of positive examples, and make sure that you understand why it makes sense to write it this way. Yeah.
So in this case, have we divided the W's by gamma?
No.
So where does the gamma come?
So I already normalized it. All I'm saying here is that it doesn't matter whether I'm writing there 1 or gamma, because I can assume that my margin is 1, and everything is going to be scaled accordingly. Or here is an example where the margin is 1. I can scale everything by gamma. Here is another example where the margin is gamma. But the behavior here is exactly the same as the behavior here, because all I did is I blew up everything by a factor of gamma.
So the weights are different.
The numbers are different, but the behavior is exactly the same. We're going to touch on this point because I know it's a confusing point, so we'll touch on it next week when we talk about SVM. But it's exactly the same. It's just scaling everything by a constant factor. Okay. So basically what you see here is 1, 2, 3, 4 algorithms, different algorithms, all written in the same way with the issue of regularization. The key point to understand here is that I didn't explain anything. All I did is I gave you algorithms. The key question here, okay, so one is this. These are all convex optimization problems. In principle, the same algorithm. Once you can differentiate, the same manner is going to get you from the loss function to the update rule. This is the more important point, which is one has to think about why does it make sense to use the size of W as a way to control simplicity. Right? So here we're using two notions of size, L2, which is sum of squares of the coordinate, L1, which is the size of absolute values, the sum of the absolute value of the coordinates. So in both cases, they measure the size of the weight vector in slightly different ways. And this makes sense as a way of simplicity or complexity of the hypothesis space. And we'll explain that, yes.
In practice, what sort of heuristics or guidelines do you use to decide which loss function to choose?
Okay, so that's next. So we're going to talk about how can we think about comparing algorithms. So in my next few slides, I'm answering your question exactly. I'm going to be a little bit extreme in this because I'm going to take two extreme families of algorithms. One is the family of additive update rules. Perceptron is a key member of it. SVM is a close relative because you could see that it's also hinge loss with some addition. And I'm going to compare multiplicative update algorithm. We know, which we just hinted on, and you will play with it also in the problem set, is the key representative, but logistic regression is also a close relative. Boosting, that we'll talk about later, is also a close relative. So how do we compare? Really what we care about is generalization. What does it mean, generalization? It means how well it's going to do in the future on previously unseen data. Now, we are dealing with linear learning algorithms. If the data is linearly separable or close to linearly separable, we know that in the limit, they are all going to learn. They're good algorithms. Eventually, they're all going to learn this. So really the key question from the perspective of generalization that we want to ask is, how long will it take? How many examples do you need in order to get to a given level of accuracy? So that's one question, one dimension of comparing algorithms. There are other dimensions. You can think about efficiency. So maybe some algorithms can be computed more efficiently than others. Maybe some of them are more robust to noise, for example, than others. Maybe some of them, or some variations of them, adapt better to new domains. So you change the distribution of the test data a little bit. Some of them will adapt faster. So these are all dimensions along which we can compare. And I'm going to focus a little bit here on the generalization dimension and try to explain compare as a function of what, right? So what does it mean I'm going to compare generalization? So one interesting way to compare is to think about properties of the data that you're going to see. And again, I'm going to be extreme to show differences. And I'm going to use as an example, just to develop intuition, the domain of a problem in natural language processing that will allow us to see that we can actually understand some characteristics of the data, and as a function of these characteristics, algorithms might behave differently. Here's the example. You've seen this before. I don't know whether to laugh or cry. I want to choose whether this type of weather or the other type of weather, the focus kind of weather. Which one should be in this context? This is a binary decision problem. I'm going to take sentences, define set of features. We talked about how to do this. You'll have a chance to exercise this understanding in the problem set. Once we define features, types of features, we're going to map each sentence to its feature-based representation. And then I generate the example or the examples that I'm going to give as input to my learning algorithm. Okay, so one important thing to note here is that there is the information that you see in your sentence, say the words around the word weather, and maybe you're not satisfied with these as your features. You may want to compute some simple functions of these words, for example, pairs of words, or maybe other functions of these words, to increase the expressivity of your function. So I'm reminding you of something that we also said several times. Why do I make this distinction between the features that you see in your data, X, and some simple functions of those? So one picture that you may have in mind is this one, blowing up the dimensionality. So it could be that relative to the local features, the function actually looks as complex as the left one, and therefore we need to transform the features to a more expressive set of features and move to the picture in the right. I'm going to show one more example, hopefully today, and you will also have a chance to play with this in your homework. Okay, so, but basically, once you think about this example here, what you can imagine is that a lot of words could appear before and after the word weather. Almost any word in English, you can construct a sentence and you will encounter sentences where each word could appear before this weather or the other type of weather. Which means that if you monitor as your features a word that appears before, a word that appears to before, a word that appears after, a word that appears to after, you will see a lot of things there. You will have a lot of features. Overall, the data set. But, so the potential, the number of potential features is very large. But I'm making two statements here, and I want to make sure that we understand. The instance space is sparse. What do I mean by the fact that the instance space is sparse? I want to make sure that we understand the terminology here. Yeah.
You have a lot of features that are not like active, so a lot of zeros in your vectors.
Right. So if my feature vector has 100,000 dimensions, dimension 1 represents the word before weather is table. Dimension 2 represents the word before weather is chair. Dimension 3, the word before table is weather is door. All these are things that I've seen in the data. But in the current sentence, they are not there. So these are Boolean features, but they are 0 in the current sentence. In the current sentence, all I have is the word before weather is no. So that feature is on. So altogether, out of the 100,000 dimensions that I may have there, only a few are going to be active on in the current example. So if I look at my examples and I write them as 100,000 dimensional Boolean vectors, very few ones are going to be there. That's what I mean by sparse instance space. Also, an independent claim, the decisions depend on a small set of features. So really, even though I extracted 100,000 features, really, I don't care about 100,000 features. The decisions, whether this is going to be weather type 1 or weather type 2, the function itself, where you to write it in the shortest possible way, it will be short. It will depend on a relatively small number of features. Whether there is door there probably doesn't matter. But maybe a few other words in the neighborhood do matter. And that's what I mean by the function space is sparse. So if you look at your W, the weights that you assign to each of these 100,000 features, most of them are going to be 0 or close to 0, which means they do not affect the decision. When you compute the dot product, they contribute nothing. and some of them are going to be relatively large. That's what I mean when I said the function space is sparse. So there is a dimensionality issue, total number of features, and there are two sparseness issues. And in the presence of this, my goal is to learn in the presence of a small number of examples relative to this dimensionality. So what can we show? And I'm not going to prove anything, I'm just going to give some intuition. So how do I measure these two issues of sparseness? One of them, let's say the target function is u. This is the weight vector that is the truth. The sparseness of the function space can be measured by the size of u. Right? So if a lot of the u's are zeros, this size of u is going to be small. If many of the components of u are non-zero, this is going to be large. Okay? This intuition is clear? The sparseness of the data is measured by the size of x. If I have very few active features, this is going to be small. If most of the features are active, this is going to be large. And it turns out that one can show that these two issues really affect generalization. It turns out that multiplicative algorithms mostly scale with this, with the size of u, with the sparsity of the feature space, the function space, and additive algorithm mostly scale with x, the sparsity in the feature space. Specifically, that's actually an important comment. This is a comment on the social science aspects of science, or machine learning in this case. For some reason, almost everyone today uses additive algorithms, Perceptron, SVM, a lot more than others. I'm not sure why. You will also not be sure why once you play with some data in your problem set, but that's the way it is, so good to keep in mind. But anyhow, so here is how we quantify them. I'm just going to give you a few formula and an example. I don't want to get into theory, but I want to give you some intuition. So these are the definitions. In case you forgot, I'm introducing how to measure sizes of vectors. On the left here, we have L1 norm, which is just the size, the sum of the absolute values. Here is L2, which is the square root of the sum of the squares of the coordinates. L infinity is just the maximal absolute value of the largest coordinate. And this is a general definition of LP. You can plug in 1 or 2 or 5 for P here. Okay, so what do we know? I'm giving two formulas. It's hard to read. Don't bother reading it. These are two bounds that we know on the number of mistakes that multiplicative algorithms like we know are going to make. So I'm going to call it MW to commemorate we know. And here it's MP for perceptron. And the key thing to notice is that really, if you think about it, this depends on this U here, the size of U. And this depends on the size of X. I'm going to give an example. It's going to be easier to see an example. I copied these formulas here, and I'm going to give you two extreme examples of a very sparse X space, a very sparse example space, and a very sparse function space, and you'll see that algorithms behave differently. Okay, extreme scenario 1. Assume that U, the target function, has exactly k features, and the rest, n minus k's, are 0. Okay? So only k input features are relevant to the prediction. Okay? So what happens if you compute this case? So L2 norm of U is square root of k. again, go to the formula and make sure that you agree with that, because I have k1s, the rest are 0. I'm summing up the 1s, taking square root, I get square root of k. Norm 1 of u is k. I'm just summing up the 1s. Max norm 2 of x is square root of n. Because I'm assuming that I could see an example where in x everything is on. I didn't say anything about sparsity of x here. I'm just talking about sparsity of u. So if you plug this in, you get that Perceptron is going to make k times n mistakes. We know is going to make k squared log n mistakes. So it's logarithmic in n, quadratic in k, which means that if n is huge, but k is small, we know it's going to make a lot less mistakes. Remember, at the end, they are all going to converge. The question is, how long is it going to take them? So this is extreme case number 1, where the target function is very sparse. I don't care about most of the features. Now, I don't know ahead of time how many features will I care about and which are the features I care about. But for analysis, I tell you, most of the features do not matter, and this gets this behavior. On the other hand, I'm going to take another extreme case where the data, where all the features matter, so U is all ones. Doesn't matter whether it's ones or 0.5 or 0.75. They are all active, they're all non-zeros. But the instances, on the other hand, the examples are very sparse. So I'm taking an extreme case, and it's a unit matrix, which means that every example is one feature on, all the rest are off. Okay? Very extreme case of sparse data. If you do the math again, and I'm going to leave this as homework for you, what you will get is that Perceptron is going to make n mistakes, the dimensionality. We know is going to make n squared ln n mistakes. So in this case, Perceptron is going to behave much better. So what is the idea? And I kind of ran through this quickly. You can go over it. My point is that even though these are very similar algorithms, eventually in the limit, they're going to learn everything, linearly separable functions. They could behave very, very differently as a function of the data characteristics. You will see something like this. I'm giving an example here that is not unlike what you will see in your homework, a little bit different because the exercise that I did here is a little bit harder than the one that you will do. Here is what I show here. I show a function that is a linear function. The function is 10 out of 100 out of n. What does it mean? Dimensionality is n. There are 100 important features. If 10 of them, any 10 of them are on, it's a positive example. If less than 10 are on, it's a negative example. Okay? So that's a linear function. And what I show here is the behavior of algorithms as a function of n. Now, as a function of n, you will notice that this function becomes sparser and sparser, right? Because n grows, but only 100 features are important. So as n becomes, I go only until 1,000, it's sparse. If it was 10,000, even sparser. What you can see is that Wino doesn't care about n. It's really logarithmic in n, which means it flattens out very quickly in terms of, I'm counting here the number of mistakes it's going to make as I run the algorithm. On the other hand, Perceptron and SVM do care about n and scale linearly. So they're going to make a lot more mistakes. Now, of course, this is a very extreme case. It's a very sparse function, but that's the idea. Okay, so with this, I think it's a good time to stop. Questions so far, actually? Yeah.
Isn't the data sparser here because the function is sparse, but the number of features that are active
Okay, so I didn't tell you what the data is, and it does not have to be sparse, because let's assume that 100 features are important. Let's take n equal 1,000, okay? 100 features are important. What do you know? What you know is that out of this 100, in the negative example, less than 10 are on. In the positive example, at least 10 are on. You don't know what happens to the other 900. It could be that many of them are on. It could be that none of them is on. So I don't know about the data sparsity here. If the data would be dense, it will favor Perceptron, as we showed in the previous slide. If the data will be sparse, it will favor Winnow, but I didn't put it into this graph. Now, in your homework, one of the things that you'll do is play with a function like this. We generated the data for you. I don't think, no, we're not giving you the ability to generate data because it's going to be too much work. What I want to do is I want to go over the homework because two reasons. One, I think it's, okay, let's see what happens. I think it's a fun homework. Hopefully you will agree. I want to encourage you to start working on it early because I don't want that, in 2 weeks, which is just a few days also before the midterms, you'll have a lot of problems. So I'm going to tell you what you have to do here, and you'll have a chance to ask questions. Now let's see. I tried this before. Let's see if I manage to get this to be readable to you. I don't see what I'm doing here, so if you have ideas, okay, let's try this. Can you see this? No? Too small? Okay. Okay, let's try this. Is this better? No. Oh, wow. Okay, what do I do here? Yeah, I just can't see what to do in order to do it. I didn't want to do this. Okay. Let's try one more thing here. Not good. Okay, that's what I can do. Sorry. You will memorize what I'm saying, and you'll remember when you look at it yourself. Those that have laptops can look at it now. Okay, so what do we have? So we have two data sets, or two types of data sets. One is synthetic data set that has two data files. One is sparse and one is dense. And another one is real data set, real life data, for the problem that you're going to solve, which is name entity recognition or some relaxation of name entity recognition, and also has two data sets. You're going to play with multiple algorithms. The key thing is that you're going to play with versions of Perceptron. 3 versions of Perceptron. The basic Perceptron algorithm. We gave you code for the basic Perceptron algorithm. Not that it's how to program, but this will give you a template that you can change for the other algorithms. The second one is we know. And the third one is other grad, which I talked about earlier. They basically are the same algorithm, you just change the update rule. So this gives you 3 algorithms. In addition, you're going to implement averaged perceptron, and you'll run it on all these 3, so this will give 6 algorithms altogether. So you'll have basic perceptron and average basic perceptron, we know in the average version, other grad in the average version. You'll get this just by implementing 2 new update rules and the averaged. And you will also use SVM as a sanity check. You will not have to program it. You will use the sklearn version. So this will give us 7 algorithms. What will you do with it? You will run, okay, so here we describe the algorithms. We talk about parameter tuning. It turns out that you don't need to tune the parameter of perceptron. You will have to tune 1 parameter for we know, and you'll have to tune 1 parameter for other grad. And we suggest values of parameters. So you'll have to do the tuning yourself, but choose among these. So this will simplify your life. And then this is the code for average perceptron, pseudocode. Again, don't implement exactly this version. Think about it a little bit and implement it in such a way that there are 2 weight vectors only. We write it there. Don't forget, otherwise it will cost you a lot of time. You don't want to do it. Okay, so, and then you run SVM. We're going to talk about SVM next week, but either way, you can just run it. Okay, experiments. So the first thing you do is parameter tuning. As we indicate there, you only have to do it for 2 algorithms. Not a lot of work, but I want you to do some parameter tuning. And we suggest how to do the tuning. Next thing, you do evaluation. And the evaluation has several components. So the first thing is you're generating a learning curve. What does it mean to generate a learning curve? We gave you a lot of examples. What you're going to do is you're going to draw 11 data points on a curve. You'll train it on 500 examples, 1,000 examples, 1,500, 2,000, up to 5,000, and then 50,000, which is the data, amount of data we gave you. You'll do it for 2 data sets. We gave you sparse data set and dense data set. And you'll do it for all 7 algorithms. So you'll have 14 curves. What does it mean to train? It means to take the algorithm with the parameters that you tuned earlier. And by training an online algorithms, 1 pass over the data is typically not enough. So I suggest here that you'll do 10 iterations over the data. Here it says 20, but in the version that you'll see online, it will say 10. It's enough. It's very fast. You can play with other numbers and see what happens. It could be interesting, but basically that's what you're going to do. So you train each one of the 6 online algorithms, and then you do the same thing for SVM, and you do it 11 times, you get a plot. In addition to this, also give us the final number, which is what you got when you train on all the data, and give us your prediction. Okay, so let me say one other thing that I missed. So we gave you 3 data sets for each data set. One is called train, one is called development, one is called test. You train on the training. When you do tuning, you use the development. You don't touch the test until the end. What you do with the test is only once you have your model, you learned everything, you run the model on the test data and give us the predictions. I think we gave you for the synthetic data 10,000 examples for test. The numbers that we will compute for you will be quite reliable on this. Now, for the test, we ask that you only run 2 algorithms, the average basic perceptron and SVM. You don't need to run all 7. Only the learning curves you'll generate on the 7. Yeah.
So what are we plotting in the learning curves?
Excuse me?
What are we plotting in the learning curves?
You're plotting accuracy of the algorithm as a function of the number of examples you trained on. So x-axis is only 500, 1,000, 1,500, 2,000, and so on. Y-axis is going to be the accuracy of the algorithm for these many examples, when trained on these many examples. Okay? That's a good question because we didn't specify exactly this. Again, x-axis is number of examples, 11 points. Y-axis is the accuracy. Yeah.
Is that accuracy only over the data we trained or the entire training?
So it's the accuracy on the development.
On development?
Yeah. So you train on training, that's it. Throw training away. You evaluate on the development set. So I think that's all specified there. Yeah.
And how do we go about cross-validation?
You don't do cross-validation here. That was previous problem set.
So so say for 50, when you take 50 examples in training, you randomly sample 50 from the training set?
No. I don't think we specified, I don't care how you get you'll never do 50, it's not enough. 500 is the smallest slice. You can sample or you can take the first 500, it doesn't matter because we generated it randomly. It doesn't matter how you do this. Given that you're going to run multiple iterations, it's going to be about the same either way you do it. Yeah?
For the plots, you said the x-axis is the number of examples trained on.
Yeah.
Where did the 11 points come from?
500 training data, 1,000 training data, 1,500 training data, 2,000 training data, all the way to 5,000. That's 10, and 50,000. And it's all specified there. So I'm just helping you to read it and encouraging you to start thinking about it earlier than Thursday next week. So that's the synthetic data. Now, then we gave you real data. And this is where I think you'll have more conceptual difficulties because we force you to do feature extraction. So here's the problem. The problem is name entity recognition. Given a sentence with words in it, for each word determine, in principle, name entity recognition is for each phrase determine whether it represents a name of a person or a location or an organization or something like this. We simplified it here, it's a binary problem. For each phrase, decide whether it represents a named entity or not. Another way you can think about it, because we're going to do it at word base, for each word, whether it belongs to an entity or not. We call it O if it's not, if it's outside an entity, or I if it's inside an entity. So it's a Boolean feature that for every word assigns I or O. So we give you a lot of sentences. You're going to break the sentences to words, and each word is going to be an example to your algorithm. A training example, development, and test example. How do you represent each word? You're going to extract features. So we suggest 7 different feature functions. You will see it there. And we actually gave you code. Okay, here's the data that you'll see. It's words with I and O. And I think this represents the feature function for the people that can see. So the feature function are the word before my target word is chair or something. The word after my target word is something. The word to before is something. The word to after is something. And then 3 conjunctions. Word before and word after are chair, door. and word -2 and word -1 is something. Word +1 and word +2 is something. 7 types of features, which means that your feature space is going to be huge as a function of how much training data we give you. We give you here a quarter of this corpus. It's called the Kernel corpus. It's still, I don't remember the numbers, they're written there. You'll get hundreds of thousands of features. But in every example, you will only have up to 7 that are on. 1 for each type, because there's only one word that appears just before the target word, and only one word that appears just after, and so on. So we coded for you 2 feature functions, I think the W-1 and the W+1. You can actually run it just with this, you'll see what you get. And it will also give you an example of how to code the other feature function. So one of the goals for me in this exercise is that you will do feature extraction. That means that for every example now, you will have a vector, a sparse vector, with 7 on things and a lot of non-off things that you don't care about. So Ascaler knows how to represent sparse examples, so I suggest you use that. If you want to do something else, you can do something else, but that's a way to do it, one way to do it at least. Here is what you will do. So you will learn just on 2 of the algorithms. Don't deal with the 7, just with averaged perceptron and with SVM. Train on the data that we give you. Evaluate on the development set. Now we give you 2 development sets. So the training data is all a collection of news that is called Kernel for the Conference of Natural Language Learning that had a shared task on this. And then we gave you 2 development sets. One sample from the same collection, Kernel, and another one from email data. It's called the Enron corpus. You will see differences in the results, which is one of the lessons here. And then we gave you 2 test data sets without the labels on which you will just run your predictors and give us the predictions. So in this case, the evaluation is very simple. You train 2 models, average prediction and SVM. You run on development, and then you run on test. Questions? Yeah?
And what's the classification telling us exactly?
So for each word, the label is I or O. I means I am part of a phrase. So Barack Obama traveled to France. I think this is the example that I'm using there as a running example. Well, in fact, there it says Obama, but let's say it was Barack Obama. So Barack will be I, Obama will be I, traveled is going to be O, to is going to be O, France is going to be O. That's the training data. Okay, so every word is labeled with either I or O. When you predict, again, you predict with respect to each word, you predict either I or O. Once you did the prediction on all the words that belong to a given sentence, you can compile it to a decision of what are the entities here, right? So take all the consecutive I's, that's a phrase, that is an entity. Now you'll see an O. Again, take all the consecutive I's, it becomes a phrase that is an entity. So you discovered what words in a sentence, or what phrases in a sentence represent named entities. Now, we only gave you features that are contextual. You only look, you sit on a word to think about whether it's an entity or not, and you only look to the sides. We did not ask you to generate features from inside the word itself, which you could. You will get pretty good numbers already with context. You could get better numbers if you look at the word itself, but you only have 10 days, and I assume you have other things to do, so that will be good enough. Yeah, there was a question. No more questions. Yeah?
So I see that the sentence data, I mean, the consecutive sentences are sort of related to each other. So do you think when I'm looking at the context for the first word in the sentence, maybe I should also look at the last word?
Okay, so we didn't ask you to do that. That's a good point. So when you sit on the first word in the sentence, it's established there. What we suggest is that for W minus 1, you just use a symbol that we called SSS for start. For W minus 2, you also use symbol SSS, just to indicate I'm the first word in the sentence. And the same thing for the last two words in the sentence that will miss two features. So you can do this. Typically for name entity recognition, looking at the previous sentence or the next sentence is not going to give you a lot of information, so that's a better thing to do. Okay, one last comment. You generate example from the training data. You will have 7 active features in each sentence. When you go to the development and when you go to the test, there will be words that you've never seen before. And therefore, you don't have features for them in your dictionary. Therefore, a development example will have less than 7 features. Right? If you've never seen a word, it doesn't have a feature. It doesn't matter whether you write the feature for it. You can still write W minus 1 equal stare, but it doesn't have a weight because when you trained, it didn't exist in your dictionary. So it doesn't have a weight. It doesn't matter whether you give it a name or not, so just drop it. So I'm just preparing you. When you do this, you will observe that some examples could be completely empty. You'll have an example. It has no active features at all. You will see a lot of it if you just run with our 2 features that we gave you. Significant fraction will be empty examples. Because we ask you to do 7 types, a small fraction will be empty, but quite a few will not have all the 7. So that's the way it is, right? So in life, some of the data you've never seen in training, and this will noisify your decision. Final question? Okay, thanks. Enjoy.
Are you going to release what the features were for the first homework?
The truth?
Yeah.
No, we were not planning to do this. If you're curious, I can probably figure it out and find it and let you know. We were not planning to do it. But we will release, we were supposed to release today actually something about the results that people got.
Okay.
Yeah.
I was just curious.
What was it?
Sure.
Last situation you talked about, the unseen wolves situation.
The what?
The last point you brought up.
Yes.
The unseen wolves.
Yeah, yeah. Come on up. I can't hear you.
Is there a good solution for that situation? Because so I'm taking NLP right now, and for unseen history, whenever there's a distribution that a different problem, they do like at-case smoothing or different types of like discounting and smoothing.
Yes.
Should we is there a similar solution to this situation?
Okay, let me just get rid of this. So sometimes you can do something. It depends on the problem. If you do power speech tagging, maybe you can have a good guess on what could the power speech tagging of the word be. I can see if it starts with CO or ends with ION, or maybe you can get a guess. In some cases, there's really very little you can do. So basically, it's kind of a problem-specific thing. In this specific case, if you will ask to get features from the word itself, then this will always be so let's say is the word doesn't begin with a capital letter? Does it end with CO? Does it start with CO? Does it end with something? So these features will be active, and you will get some information about the word, even though you've never seen the word before. But given that I only ask you to do context features, there's actually little you can do. You will ignore it in this case. Now, you're welcome to try if you other features that will not disappear. And we'll see what happens. Yes. You can add more features. What we ask is just the minimum because we'll be able to get some comparison. But yeah, it's in fact, I think we wrote there that you can do other experiments. I don't think we wrote it specifically for the real data, but you can try it also for the real data.
What's the difference between synthetic data and real data, and how's the difference going to affect it?
So the real data is real. I mean, it's really newspaper articles that we solve the real problem. The synthetic data, we invented the function, and we kind of massaged it so that you will see something that I want you to learn. I want you to see. Now, in real data is a mix of a lot of phenomena. So you don't always see things in such a clean way as in synthetic data. From the perspective of the algorithm doesn't care what you want it on.
Okay, so we don't have to like bring up the difference.
No, but you will see in the synthetic data you get nice numbers, nicer than in the real data because it's clean. It's noisy. I forgot to say we actually added noise to it, but you'll see it written there. It basically is data that was generated to make a point. And the news data, I'd like to generate it so that I make a point, but I didn't generate it. So, sure.
Hi. Just a quick administrative question. I sent you an email, I think last week, like the end of the week, about potentially switching to 519 from 419.
And I responded to you and CC'd Nick.
Yep, and he got back to me, so I stopped by the office.
Yeah.
And they said it's pretty straightforward. It's like kind of annoying because you have to fill out a couple of petitions. But basically, if you're okay
I
with
can
it,
sign it.
cool.
Yeah.
I think this is the one. Where it
So
says
which direction did you want to go?
from 419 to 519. And I think you just need to sign, put name here. So the only difference is really going to be the project, right?
Okay.
Awesome. Thank you so much. Appreciate it.